Welcome to lesson 11, the NFTs lesson. Now for the Chainlink YouTube version of the freeCodeCamp videos, this is actually our last one. And the reason this is our last one is because the next two are a little bit more optional. Upgradable smart contracts are definitely an advanced feature and something that takes a little bit more finesse. If you want to see some more videos and some more tutorials on upgradability, definitely check the GitHub description for some videos on how to do that. Additionally, right after that, we actually do a full stack demonstration. We're constantly putting out more and more full stack demonstrations on how to build a front end, how to build a website using these blockchain applications. There's tons of different ways to do these, and we're coming out with more and more every single day, and there's really no one correct way to do it. So for now, this is going to be the last one, and this is going to be on NFTs, or non-fungible tokens, something that has surprisingly taken the world by storm. And these are an absolute blast to make, and you can make some really, really cool and really interesting applications with these, especially with Chainlink. So with that being said, I'll let you jump in and I'll let you dive in, but keep in mind, we've actually done a number of these demonstrations, a number of these applications using different protocols and different ideas, and there's just so many unique things you can do with this. So I'll leave it to you with how to do it and how to move forward. But for now, let's learn about NFTs. NFT stands for non-fungible token and is a token standard similar to the ERC20. Again, ERC20 is like Link, Aave, Maker, all those goodies that are found on the Ethereum chain. An NFT, or a non-fungible token, is a token that is non-fungible. This means that they are starkly unique from each other, and one token isn't interchangeable with any other token of its class. A good way to think about it is $1 is interchangeable with any other dollar. $1 is going to have the same value of another dollar. Those are fungible tokens. That's like ERC20s. One link is always going to be equivalent to one other link. By contrast is going to be NFTs. Those of you nerds out there would know, like a Pokemon would be a good example of an NFT. Your one Pokemon is going to have different stats, different move sets, and isn't interchangeable with any other Pokemon. Or maybe a more relatable one is like a trading card, a unique piece of art, or the like. So that's what these NFTs are. They are non-fungible, non-interchangeable tokens that for the moment are best represented or thought about as digital pieces of art that are incorruptible and have a permanent history of who's owned them, who's deployed them, etc. Now, like I said, NFTs are just a token standard. So you can actually make them do much more than just be art. You can give them stats, you can make them battle, you can do really unique things with them, you can do pretty much whatever you want with them. But right now, the easiest way to think about it, and the most popular way to think about it, is by calling them art. 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 It's art! Or some type of collectible, or just anything that's unique. Now, they've been getting a ton of buzz recently because we've been seeing more and more of these being sold at insane prices. Like we saw Axie Infinity sell 9 plots of their land, 9 plots of their unique land for $1.5 million. We also saw the original creator of the Neon Cat, you know this cat, sold for like 300 ETH. So like I said, they're just tokens that are deployed on a smart contract platform, and you can view them on different NFT platforms like OpenSea or Verifiable. And these are the NFT marketplaces that let people buy and sell them. You obviously can do that without these marketplaces because it's decentralized, but they help and give a good user interface. So that's the basic gist of it. Let's talk some more about the standards. The ERC 721 standard, or the NFT standard. This is the basis of it all. There is another standard that's semi-fungible tokens, the 1155. We're not going to talk about that here, but you can check it out. The main differences between a 721 and an ERC20, on ERC20s, they have a really simple mapping between an address and how much that address holds. 721s have unique token IDs. Each token ID has a unique owner. And in addition, they have what's called a token URI, which we'll talk about in a minute. Each token is unique. Each token ID represents a unique asset. So since these assets are unique and we want to be able to visualize them and show what they actually look like, we need to define those attributes of the object. If it's a piece of art, we need a way to define what that art looks like. If it's some type of character in a game, we need a way to define that character's stats in the NFT. This is where metadata and token URIs come in. So if you know anything about Ethereum, you know that sometimes gas prices can get pretty high, especially when it comes to storing a lot of space. It can get really, really expensive. So one of your first questions might be, well, are they storing these images and these art pieces on chain? And the answer is sometimes. Back when they were coming up with NFTs and artists were deploying stuff, the ETH devs and the artists were like, yeah, art, let's do that art. I'm just gonna deploy this 1 megabyte image onto the Ethereum chain, and oh God, it's so much gas expensive. How do I delete fine? How do I? It's not deleting. And they realized that if they put all this art on chain, it was going to be incredibly expensive. So to get around this, what they did is they put in the standard what's called a token URI. This is a universally unique indicator of what that asset or what that token looks like and what the attributes of that token are. And you can use something like a centralized API or IPFS to actually get that token URI. Typical token URI has to return something in this format like this, where it has the name, the image location, the description, and then any attributes below. Now, if you're like me, your first question would probably be,
we pull from a single source seems pretty centralized.
This is a current limitation of the NFT ecosystem. There is often this talk of on-chain metadata versus off-chain metadata. Because it is so much easier and cheaper to store all your metadata off-chain, a lot of people will use something like IPFS that is decentralized, but does take a little bit of centrality to keep persisting, but they can also use their own centralized API. However, obviously, if that goes down, then you lose your image, you lose everything associated with your NFT. Because of this, most NFT marketplaces actually can't and won't read off on-chain attributes or on-chain metadata because they're so used to looking for the token URI. Obviously, if you do off-chain metadata, you can't do anything really cool or really interesting or have any games with your NFTs. For example, if you wanted to create an on-chain Pokemon game, all your attributes would need to be on-chain in order for your Pokemon to interact with each other. Because if it was off-chain, then that becomes a lot harder to cryptographically prove. So if you're new with NFTs and you're like, wait, this is kind of a lot of information, I'll make it easy for you. If you're looking to render an image of an NFT, add your image to IPFS, add a metadata file pointing to that image file on IPFS, and then grab that token URI and put it and set it as your NFT. The Chainlink D&D article does a great job of walking you through this and showing you how to do this, so be sure to read that if you're looking to learn how to do that.
So all the code that we're going to be working with is actually available for you in this NFT mix, Brownie Mix. It's an official Brownie Mix, and it allows us to deploy these 3 adorably cute dogs. And there are 2 different types of contracts that we're going to be working with. We're going to be first working with a simple collectible, and then we're going to work with an advanced collectible. The simple collectible is going to be a very simple ERC 721 standard. We're not going to really add any bells and whistles other than give it like a name. And then our advanced collectible is going to take advantage of some of those more advanced true scarcity features that we were talking about. So protocols like Avagochi and Ether cards use Chainlink VRF to get verifiably random numbers to create verifiably scarce NFTs. Something that's important to keep in mind is that in the real world, when companies create trading cards, there's no way to prove how scarce or how valuable these trading cards actually are. If we use a verifiable random number, then whoever is deploying these NFTs can't even control how rare these NFTs really are. So we get this verifiable scarcity and this verifiable rarity, which add some value to the tokens. If you want to just go ahead and work right from the Brownie Mix, you can absolutely just run Brownie bake NFT mix and then CD into NFT. And all of our code is going to be right in here. We're going to go through and deploy and develop everything from scratch because we're going to actually take some previous concepts that we've learned, improve on them, and we're going to learn a lot of nitty-gritty, interesting pieces about making this hybrid smart contract, because these NFTs really are a perfect example of a hybrid smart contract. They have some off-chain component interaction with a random number and we're storing their metadata with IPFS. And I'll explain IPFS a little bit more in depth as we go on here. So let's go ahead and get to it. I'm going to go ahead and make a new directory called NFT demo. I'm going to CD into it, code, period. And perfect. I have a blank project here, and you already know what the first step we're going to do is do Brownie init to create our blank Brownie repository. Now let's go ahead and create our first contract. We'll call this simple collectible.sol. Since this is going to be a simple collectible, a simple NFT that we're going to get started with. Now, similar to the ERC20, this ERC 721 standard has a number of functions that we can actually work with. We can go ahead and even look at the ERC 721 non-fungible token standard on the eips.ethereum.org website. And we can see a sample interface and some sample events and some functions and kind of everything that we've grown to know and love. And once again, instead of us kind of recoding, copy pasting all of this from scratch, we're going to be using OpenZeppelin's ERC 721 documentation for this. Now we're going to be working with version 3.x. There is a version 4.x that has come out. Using version 3.x of their OpenZeppelin contracts is also, I think, a little bit easier to explain. But again, those of you who want to challenge yourself, definitely try their 4.x version. So let's go ahead and jump right into it. First, we'll do our SPDX license identifier, MIT. Then we'll choose our Solidity version. We're going to use Pragma Solidity 0.6.6. But again, most of this should work for 0.8 moving forward. And then we're going to go ahead and look at the OpenZeppelin ERC 721 documentation. And we're going to go ahead and grab this line right here. Import OpenZeppelin/contracts token ERC 721, ERC 721.sol. You can even see a sample ERC 721 that they give you. And this is actually going to be similar to the ERC 721 that we're going to make. So we're going to go ahead and paste that. And of course, since we're doing this at OpenZeppelin/contracts, we're going to need to create our Brownie config. And same as always, dependencies. It's going to be OpenZeppelin/OpenZeppelin contracts. And again, like I said, we're using version 3. So 3.4.0 again. And then we'll do compiler, sulk, remappings, and we'll say at OpenZeppelin equals this. And great, let's even try to just compile this right now. Brownie compile. And perfect, it has been compiled. Now, similarly to our ERC20 that we did with OpenZeppelin, we're gonna do the same startup here. So we're gonna say contract, simple collectible is ERC 721. And this is how we're going to inherit all of those functions in the ERC 721 token standard here. And we can start coding our simple ERC 721. Now for our ERC 721, we're gonna make it be a couple of these cute, adorable dogs. So it's gonna be one of these 3 dogs. For our simple collectible, we're just gonna go ahead and use the pug here. So you can use any image that you want for this demo. However, if you want to just follow along with us, we can just download this dog and we'll call it pug, create a new folder here called img. And then I'm just going to add pug.png to this img folder. So this is going to be the NFT that we're going to deploy. We're going to deploy this very simple pug for our smart contract. So we're going to be deploying this pug. This is the image that we're going to use for our NFT. It's going to be this adorable pug. So let's go ahead and create the rest of the contract for this pug. So the first thing we're going to make is our constructor. It's going to take no input parameters. It's going to be a public constructor. And then we're going to go ahead and use the ERC 721 constructor, which if we look at the documentation, we give it a name and then a symbol. We're going to use the ERC 721 constructor parameters, which is going to be a name, which we're going to say is doggy, and a symbol, which we're going to say is dog. And perfect. That's all we really need to do for the first part. This NFT contract is actually what's known as a factory contract. There's a main contract, and in it, it has a list of all the NFTs and the owners that are of this type of NFT. So in this example, all of the type of NFT is just going to be this pug, and it's just going to be this dog. And we actually need a function to mint new NFTs based off of this pug. Now we can absolutely have an NFT factory contract that only creates one single NFT, but we're going to use this factory implementation to create multiple NFTs. We're going to do it with a function called createCollectible. This will create a new NFT and assign it to whoever called this function. So anybody can come here and create a new puppy for themselves, or in other words, adopt a puppy. So we're going to say function create collectible public. and we're going to say returns uint256. You'll see why we need to do this in a minute. Now, when we create this collectible, all we're doing is we're assigning a new token ID to a new owner. And if we look at the OpenZeppelin ERC721 GitHub, we can see they have this safe mint function. This is the function that they use to mint or create a new NFT. This function, it takes a new address to, which is going to be the new owner of the NFT, and a token ID. Every NFT in this factory contract has a unique token ID. We're going to have our token IDs start from 0 and just increment every time we have a new token minted. This safe mint function calls this safe mint function, which calls this minting function. So if you're looking at the code here, this mint function is really the function that calls and creates this NFT. You'll see actually that they just have two mappings that they update. They update this owner's mapping, which is just a mapping of token IDs to the owners of the token IDs. And then they update this balances mapping, which is a mapping of owner address to the token count. So the number of tokens that an owner actually has. And that's all that's happening when we call this mint, or in our case, safe mint function. The difference between safe mint and mint is safe mint checks to see if a token ID has already been used or not. And this way we don't actually override who owns tokens and who owns token IDs. So we're going to use the safe mint function. So first we need to think, okay, well, we're going to need a way to count these token IDs so that every single person has a unique token ID. So let's create a global variable, uint256 public token counter, and we'll initialize it, token counter, to 0. Of course, this is the same as initializing token counter to 0, but let's just make it very explicit. So when we create a new collectible, we're going to say uint256 new token ID is going to be equal to this token counter. And we're going to iterate this every time we mint a new token. So for example, we're going to iterate that in this create collectible here. So new token ID equals token counter. We're going to call this safe mint function, since we're inheriting it from OpenZeppelin's ERC721. We need to give it this new NFT, an owner, which is going to be message.sender, so whoever calls this function. And then we need to give it a unique token ID, which is going to be this new token ID. Now, whenever we mint one, we're going to want to increment this token counter. So then we can say token counter equals token counter plus 1. And we can then return this new token ID. So we'll return the token ID of the token that we just created. And boom. If you're looking for an incredibly minimalistic contract to deploy NFTs, this is all that you need. So we can run Brownie compile to make sure we did everything right. And product has been compiled. We can see it in the build, so great job. Obviously, this might be a little dissatisfying to you after the breakdown that we just gave. How do we view this token? What does this token look like? I thought we wanted this to be a doggy. How do we know that this looks like a dog? How do we get this image on the blockchain? This is where metadata is going to come into play. Now, if we look at the original ERC721, there is this part called the metadata extension is optional for ERC721 smart contracts. As we've talked about, anytime you make a transaction on chain, it costs some gas. Even very tiny amounts of data can cost more and more gas. Images are much bigger than these little bits of data here, and they can cost a lot more gas. So when this standard was being created, the developers kept this in mind and knew that storing entire images and entire GIFs and entire videos on chain was going to be incredibly costly. So they added this piece about metadatas and token URIs. The token URI is a distinct uniform resource identifier for a given asset. This is an example of a URI and the metadata that we're going to be demoing today. A URI is just a unique resource identifier. So this can be something like HTTPS or IPFS or any URL string that uniquely points to some metadata. Your metadata file is going to look like this. It's going to have a title for the title of the NFT. It can have a type, and it can have all these different properties or stats or attributes. For example, we're going to have our pug NFT, which is going to be defined like this. It's going to have a name as pug. Description is going to be an adorable pug pup. And it's going to have what's called the image URI, which defines what the token actually looks like. And if we copy paste this into another browser, we get returned this. It's this token URI with this metadata JSON object that's going to enable different NFT platforms to actually render our NFT. So this is an example of what this pug is going to look like on different NFT marketplaces like OpenSea. Platforms like OpenSea understand that they need to show this image, they need to use this name, they need to use this description and have these traits. So if we look back at this NFT on OpenSea, we can see the name is pug. We can see the description here. If we go to levels, we see its cuteness is 100 out of 100. Now this of course leads us to a really interesting point. If we're storing the image off-chain, then how is this image decentralized? If we're storing this image off-chain, how can we guarantee this NFT is going to stay forever? Now, this leads us into a little tidbit about storing data on the blockchain. As of current recording, storing a lot of data on-chain can get incredibly expensive. The more data that you store, the more transactions that you have to make to store that data on-chain, and the more gas that you're going to have to spend. At the time of recording, Ethereum is about little less than 900 gigabytes in size. If a ton of people were to put full videos or movies or massive images, Ethereum would grow exponentially out of proportion. And this would become unsustainable for the blockchain network as a whole. So Ethereum isn't great for actually storing a ton of data. It can store a lot of data, but it's a lot better for doing the logic and the smart contracts. So there are a lot of different platforms that are actually working on this problem of storage. These platforms allow people to store data in a decentralized way that isn't going to exponentially explode the size of Ethereum or different smart contract platforms. The decentralized storage methodology we're going to work with is going to be IPFS, or Interplanetary File System. And this is where we're actually going to store our image, and this is actually where we're going to store our image so that NFT marketplaces know what our NFT looks like. Now, here's what some protocols do. Some protocols just set up a server and set this token URI to instead be from a decentralized service like IPFS and use just maybe their own centralized server. This is obviously a massive issue because if their server goes down or if they want to change the image or they want to change the stats, all they have to do is change it in their server. And this is why a protocol like IPFS is going to be a lot easier, quicker, and more decentralized version of doing this. The full solution is going to be using something with IPFS and Filecoin, but easy solutions to do that are still being built out. So for now, we're just going to use IPFS because it's free, it's quick, and it's easy. And it can be expanded to combine with Filecoin to be even easier to work with. Now, something else that I want to touch on too. When it comes to this metadata, right now, all these NFT marketplaces only know how to pull attributes from this token URI. Now, if we want to build really cool NFTs that can interact with each other, having some attributes or maybe some like attack stats or attack moves like in Pokemon, for example, or trading cards, we can't just store these in this token URI because the blockchain doesn't know anything about this token URI. So we actually need to store these attributes on chain. I'm really hoping in the future, a lot of these NFT marketplaces are going to get better at and pulling metadata from on-chain. But right now, any attribute that we give our NFTs, we actually have to reproduce in the token metadata and the token URI as well. So we've just learned a lot about metadata, IPFS, token URIs, and everything like that. Let's update this simple NFT to be able to render on OpenSea and render on these NFT platforms. Because right now, if we were to deploy this, nobody would know what this doggy looks like. So let's give it a token URI. So in this create collectible, let's do string memory token URI. And after we call this safe mint function, there's another function that we're importing called set token URI. And we're going to set the token URI for the token ID. And we're going to give it this token URI. This will allow our NFT to actually have an image associated with it that we can actually see. So let's go ahead and create a script that's going to deploy this NFT factory contract and then create us a collectible. So we're going to do new file. We'll call it deploy and create.py. And let's jump into our script. So we'll do def main. First, we need to start with an account. And once again, we can go ahead and create helpful scripts.py. We can go ahead and copy paste this get account function in here if you want. But of course, since we added this config wallet from key, we're going to go to our Brownie config. We'll add wallets from key, and we're going to grab our private key environment variable. Since we're using a private key, again, we're going to create a .env, and we need to export private key, and we're also going to need to export our Web3 Infura project ID. So we can just copy paste from our last project, the private key, Web3 Infura project ID, and our Etherscan token so that we can actually verify this on chain. And we'll add a new file, init.py, so that older versions of Python know that this is indeed a package. So we'll go ahead and do from scripts.helpful scripts import get account. Now all we have to do is import our simple collectible and run simple collectible equals simple collectible dot deploy. And if we look at our simple collectible, we have no constructor parameters here, so we can just do from account. And now this will have our simple collectible deployed. Now we need to actually call this. Now we actually need to call this create collectible function, and we're going to pass it a string, which is going to be this token URI. I'm going to go ahead and use this sample token URI that is included in our NFT mix. So if you're looking to get this token URI, look up NFT mix, Patrick Collins. Hopefully the GitHub will show right up, and we can just go right to the scripts in here in the simple collectible folder, create collectible. That was the big free. And we're going to grab this, and in our script, we're going to do sample token URI equals this. Now, when you paste this token URI in your browser, if you can't see it, you might have to add something like IPFS companion to your browser like this. Some browsers don't natively have it. So there is a link to IPFS companion for this project in the GitHub repo. But now that we have a token URI, we can call this create collectible function. So we'll do transaction equals simple collectible dot create collectible, and we'll pass in this sample token URI, and then of course we'll do from account. We'll do tx.wait. We'll wait for one block, and then if we've done this correctly, we'll actually be able to see this NFT on an NFT marketplace like OpenSea. So let's do a quick print line here. We'll do print. Awesome. You can view your NFT at, and we'll do this in F string. And this is where we're going to put the OpenSea URL for this Rinkby. So we're going to say OpenSea URL, which is going to be equal to, if we pop over to OpenSea, if we pop over to this OpenSea pug here on the Rinkby testnet, we can go ahead and grab this first start of the string. So it's going to be https testnets.opensea.io/assets. And then this is the address of the contract. So we can say OpenSea URL is going to be this /, and we'll put this little brackets here, /, and then another one of these. And this is because the URL for here, testnets.opensea.io/assets, it's the contract address, and then the token ID on the end here. So this is what it's going to look like. So in our print line, awesome, you can view your NFT, OpenSea.format, simple collectible.address, comma, and we can do simple collectible dot token counter -1 for the most recently deployed one. And then we'll run this now. Brownie runs scripts, deploy and create, network, Rinkeby. And awesome, we get this print line here saying Awesome. You can view your NFT at https://testnets.opensea.io. Just keep in mind, obviously for mainnet, we can't use this testnets.opensea.io, but assets, the address of the NFT contract, and then the token ID as well. So if we go ahead and click this, and it looks like it's already actually been rendered here in OpenSea. We could even go ahead and hit refresh metadata just in case it doesn't show up right away, but it looks like for us, it did show up right away, which is awesome. Some other kind of fun parts about OpenSea is if we go to our profile here, we'll actually be able to see all of the NFTs that we own on this testnet. I've actually deployed this doggy twice here, once to test and then once to actually do it. Great, we've created our simple collectible. Of course, no project is complete without some tests. So let's create some tests. Since we're also going to be doing an advanced collectible, I'm going to skip the integration test and I'm just going to write a really simple unit test. So we'll create a new folder, we'll call it unit. And in here, we'll do a new file, test, simple collectible.py. So let's create our first test. We'll do def test can create simple collectible. We'll just make sure that we can actually create a simple collectible. Now we'll make sure that this is our unit tests. So we'll do from scripts.helpful scripts, import local blockchain environments. And then we'll do if network.show active, not in local blockchain environments, pytest.skip. So of course we need to do from brownie, import network, and then also import pytest. Now, something that we could do here is actually in our test, we could go ahead and even test our scripts by importing deploy and create here and testing this. We could do something like return simple collectible. And in our test, then we could do from scripts dot deploy and create, import, deploy and create. And then back in our deploy and create script, we can modify this a little bit. Instead of main here, we'll call this deploy and create. And then we'll have our main function just call deploy and create. And you'll see brownie run scripts, deploy and create to Pi. If we go ahead and run this, again, we can just run this on the development network real quick instead of on Rinkby. You'll see that this does also work. Obviously, we won't actually be able to see our NFT on OpenSea because this is deployed to the Brownie temporary Ganache chain as opposed to a persistent Rinkby chain. In our test here, we could then just run simple collectible equals deploy and create. And then we'll do an assert here. We'll assert simple collectible dot owner of 0 is going to be equal to get account. And then we'll also import get account. So we can run Brownie test, make sure this works, and perfect. Now, this was all fun and dandy, but there's a couple of things that we didn't go over and that we didn't do. So let's create a quick readme.md for a couple of notes. So number one, we didn't upload an image to IPFS ourselves. So we just used a token URI that was already existing, right? We didn't actually upload something to IPFS. We didn't go over why is IPFS decentralized. We didn't really talk too much about what IPFS is. Number three, anyone can mint an NFT here with any type of stats, right? It's not verifiably scarce or random, right? This isn't that cool. So we want to actually build an NFT project that has all these pieces where we upload the image to IPFS ourselves. We're going to talk a little bit more about why IPFS is decentralized and it's the preferred solution for storing NFT metadata. And we're going to make our NFT more verifiably random and verifiably scarce, like for things like Ether cards and Avagochi. Let's go ahead and do this project again, but we'll integrate the Chainlink VRF to make this NFT verifiably scarce and verifiably random. And then we'll also teach you guys how to upload to IPFS and work with IPFS ourselves. So let's go ahead and do this. So let's create a new file in our contracts and we'll call it advanced collectible.sol. And what we're going to do here is we're going to make, again, an NFT contract where the token URI can be one of 3 different dogs. So if we look at this NFT mix, in the images section, there's a pug, a Shiba Inu, and a Saint Bernard, or one of these 3 dogs. We're gonna make it so that when you mint one of these NFTs, you're gonna get a random one of these 3 dogs. Now, I'm not gonna go over stat generation and like creating battling NFTs or really games out of these NFTs. If you guys wanna see a version of those contracts, check out this Dungeons and Dragons NFT. There's a link in the GitHub to see this. And it actually creates characters that can do battle and have like stats and attributes like attack, constitution, and different things you'd find in Dungeons and Dragons. This one's done actually with Truffle as opposed to being done with Brownie, but all the contracts are going to be the same other than this migrations.sol. So if you're looking to check this out, you absolutely can. It is a ton of fun. And they have some really cool images as well. So be sure to check that out if you're looking for more. Anyways, here's what we're going to be looking to do. We're going to make an NFT contract where the token URI can be one of 3 different types of dogs, and it's going to be randomly selected. So let's go ahead and do it. So first, again, we're going to do this SPX license identifier right at the top. So we can go ahead and put that there. And we're going to even use same Solidity version, and we're going to use OpenZeppelin again. So we can literally just copy and paste that from our last project. Now we're going to create our contract, advanced collectible. We're going to say is ERC 721. Great. And then, since we're going to want to work with Chainlink VRF to get a provably random NFT, we're also going to want to import at chainlink/contracts/src v0.6 VRF consumer base.sol. And of course, that means we're going to go back to here and we're going to add smart contract kit /Chainlink Brownie contracts at 1.1.1. And then we're going to go ahead and add the remapping in. We'll say at Chainlink equals, boom. Awesome. So we've imported the Chainlink bit. Our advanced collectible is ERC 721, and it's going to be VRF consumer base. So same as always, let's go ahead and start with the constructor. We know from our lottery smart contract that we're actually going to want to parameterize a lot of these pieces for working with the VRF coordinator for working on different chains and different testnets. So we're going to do address VRF coordinator. We're going to do address link token bytes 32 key hash. And we can always head back over to docs.chain.link, go to get a random number, just in case we forget what some of the parameters are. VRF coordinator, link token, key hash, and fee. Great. You went 256 feet. And we'll make this public as well. Add a little curly bracket there. And we can go ahead and start doing the rest of this. Of course, we need to do the VRF consumer base constructor and the ERC 721 constructor. So VRF consumer base is going to be this VRF coordinator and this link token and the ERC 721. We could parameterize these as well, but we know it's going to be a dog, so we'll do doggy and the symbol of dog, which is the same as our simple collectible here. We know we're also going to need to do this token counter bit. So we'll do UN256 token counter. And right in here, we're going to do token counter equals 0. Of course, we're going to need a key hash. So let's make this UN256 public token counter. Excuse me. We're going to do a bytes 32 public key hash. And we're going to do a UN256 public fee. And we'll set key hash equals key hash and fee equals fee. Great. So this is a combination of a lot of the stuff we did in our lottery smart contract and some of the pieces that from our ERC 721. We need the key hash, the fee, VRF coordinator, link token, all for the VRF consumer base. Oops, I should put an extra quote here. And then we need dog, doggy, and a token counter for our ERC 721. So now we're going to create our function create collectible. So we're going to do function create collectible. And again, we're going to do a string memory token URI. But this time in our Python scripts, we're actually going to define where we're getting this token URI from, and we're going to create it ourselves. But we're going to make this public, and it's going to return a bytes 32. Remember way back in our lottery, when we did this event requested lottery winner, when we called the Chainlink VRF, we're going to do a similar thing here where we're going to make an event for whenever we request one of these new dogs. And that is also what we're going to return. We're going to return that request ID here. So since we're using the Chainlink VRF here, we can go ahead and call that request randomness function, which again, head over to the docs.chain.link. This is imported from the ERC 721. And then in that request and receive model, it's going to call back with our fulfill randomness function. We're going to need to do a couple of different things here because we want the user who called to create collectible to be the same user who gets assigned the token ID. So first we'll do bytes 32 request ID equals request randomness. And we're going to pass obviously the key hash and the fee. This is going to create our randomness request to get a random breed for our dogs. So let's go ahead and just define a little bit of the fulfill randomness function so we can figure out how we're actually going to pick a random dog. Well, the first thing that we're going to need is we're going to need some definition of what the different breeds that the dog can actually be. And again, similar to the lottery, we're going to create a new type called breed using the enum. So we're going to do enum breed, and then we're going to give it 3 types. Pug, which is going to be state 0, Shiba Inu, which is going to be state 1, and Saint Bernard, which is going to be state 3. So our breed is going to be one of these 3 breeds here. So then in our function fulfill randomness, when we get that random number back, we can use that random number to pick one of these 3 breeds. So of course we need to have a bytes 32 request ID and uint256 random number. And we're going to make this internal override so that only the VRF coordinator can call this. And what we're going to do now is we're going to select a breed based off of this random number. So we're going to say breed, which we're saying this breed variable is of type breed. It's going to be equal to breed generated from that random number mod 3. Since we have 1, 2, 3 different breeds. Awesome. So this is how we're going to get our random breed. However, we do need to assign this breed to its token ID. So now that we have a random breed back, how do we actually go ahead and assign this? Well, we're going to have to create a mapping to do this. It'll look something like token ID to breed. We're going to have to get our token ID somehow, and we're going to have to equal it to the breed. So then our first question is, okay, well, in order for us to assign this breed to the token ID, how do we actually get the token ID? Well, we're going to grab the token ID by doing uint256 new token ID equals token counter. And then we'll just set the token ID to breed using this new token ID equal to the breed. So we're going to want to make this token ID to breed mapping up here, to which we can do mapping uint256 map to breed, and we'll call it token ID to breed. This way, each token ID is going to have a very specific breed based off of this mapping's results. Perfect. Okay, what else do we need in this fulfillment? We need to mint the NFT, and we need to set a token URI. Well, when we minted it before, we called this safe mint function. However, message.sender here is always going to be the VRF coordinator, since the VRF coordinator is actually the one calling this fulfill randomness. So we can't actually have this just be message.sender. We need to figure out how we can get the original caller of create collectible here. How do we get the original message.sender of create collectible? Well, the answer there is actually going to be in another mapping. When we call create collectible, we can create a mapping of request ID to sender. And this is going to take the request ID as a key, and then whoever sent it as the value. So we're going to create this new mapping at the top. And then actually let's make this other mapping public as well. We'll do mapping bytes 32 to address. We'll call this public request ID to sender. Now in our fulfill function, the same request ID that requested the random breed is returned. So what we can do is we can say address owner or sender is going to equal request ID to sender of request ID. And then this address owner is who we're going to safe mint the NFT to. And of course, while we're matching up the functions, we don't want to forget to always do token counter equals token counter plus 1 at the end. Awesome. Now we still need to set the token URI here. So back in our advanced collectible, we're going to have to do this set token URI at some point. So let's actually think about this for a second. We're only going to know breed of our dog once this random number is returned. And we know the breed of the dog is going to be one of these three breeds. It's going to be a pug, a Shiba Inu, or a Saint Bernard. And let's actually, for now, let's even just go ahead and add those three images to our project here. Create a new folder. We'll call it image. And you can put whatever images you want in here. I'm actually just going to download the three images right from the NFT mix. Boom. And now I have my pug, my Shiba Inu, and my Saint Bernard in here. So anyways, it's going to be a pug, a Shiba Inu, or a Saint Bernard here. We're only going to know what the breed is once the random number is returned. And the breed is actually going to govern if it's a pug, Shiba Inu, or a Saint Bernard. So we technically could actually just get rid of the input parameters for create collectible, since there's going to be no token URI initially created. What we could do is we could create a new set token URI function that sets the token URI based on the breed of the dog. For the simplicity of this project, we're actually just going to create our own set token URI function that we're going to update based off the breed of the dog. A challenge for you after we finish this project is to make this even more decentralized and have the fulfill randomness function actually be the one to decide what the token URI is. But for now, in our fulfill randomness function, we're going to skip setting the token URI, and we're actually going to call it in a separate function. We're going to create our own function called set token URI, and we're going to pass it a uint256 token ID, a string memory token URI. And we're going to make this a public function. Once this fulfill randomness function is responded, the breed of the dog is going to be set, right? This token ID to breed is going to say, hey, this token ID now is associated with this breed, which is going to be pug, Shiba Inu, or Saint Bernard. All we want to do then is, now that we have the on-chain metadata, we're just going to reciprocate that with the off-chain metadata. So we're going to need 3 token URIs for those 3 dogs. We're going to need one for pug, Shiba Inu, and then obviously Saint Bernard. However, we want to make it so that only the owner of the token ID can actually be the one to update the token URI. So we can use a require function for this. We can say require, and we're going to use an imported OpenZeppelin function called isApproved or owner message sender token ID. And we're going to do a comma here, ERC 721 caller is not owner nor approved. This is approved or owner function, if we go into the ERC 721 GitHub for OpenZeppelin, we can find this function is approved or owner, which checks the owner of the ERC 721 of that token ID. And it makes it so that only the owner or somebody approved to work with this token ID can actually change the token URI. So then we're just going to call that function called set token URI of the token ID and the token URI. Now we're actually manually going to be the ones to call this set token URI once the breed has been decided. We could, of course, like I said, use a mapping at the top that automatically routes it there, but so that we can experiment a little bit more and learn a little bit more about IPFS, we're going to leave it a little bit more general like this. And perfect. This is pretty much the majority of what we're going to need for our ERC 721 contract. Obviously, we still need to work with IPFS and getting our token URI, but for the most part, this is everything that we need. Now, I am going to introduce a new best practice here. Whenever we update a mapping, typically a good best practice is going to actually be to emit an event. So let's create an event for each one of these mapping updates. We'll call it event requested collectible, and we'll do a bytes 32 indexed request ID, and we'll also do a address requester. This requested collectible event is going to be emitted when we request ID to sender because we're updating the mapping here. This is also going to be really helpful when we run our tests so we can get this request ID, similar to what we did with the lottery. So down here, we're going to do emit requested collectible. Let's collectible here. Let's use an I instead of an A here. Collectible. And we'll pass it this request ID and then message.sender. We also update a mapping down here with token ID to breed. So we're going to do a new event. We're going to call event breed assigned. And we'll do a uint 256 indexed token ID. And then we'll do a breed. And then when we assign the breed here, we're going to emit breed assigned with new token ID and breed. So let's see if we did everything right. Let's do Brownie compile. Looks like we have a quick error here. Did you mean fee or fee? Let's do a quick underscore there. Now let's try to compile. Much nicer. All right, great. Let's move on. All right, so now let's take a little look-see at our scripts here. So we have this deploy and create script, which is going to work for our simple collectible. So let's go ahead and actually give them both their own folder. So we're going to do a new folder. We'll call one simple collectible. And we'll do another new folder called advanced collectible. And we'll grab this original deploy and create, and we'll place it into this simple collectible folder here. Awesome. Now, if we wanted to run this, we would do Brownie run scripts, simple collectible, deploy and create, and we can go ahead and test this out on our local ganache here. And cool, looks like it's working correctly. Great. So now let's create our advanced collectible script. And a lot of what we're going to do is going to be the same as this simple one, deploy and create. So I'm actually going to copy this. We're going to create a new file called deploy and create.py. We're going to paste everything in here. But we are going to change a couple things up. So let's do a little bit of refactoring first. So this OpenSea URL, we're going to be accessing in a couple of different scripts. So we're actually going to take this, copy it, get rid of it in our deploy and create here. And we're going to move it to our helpful scripts and place it under here. OpenSea URL equals this script right here. And now what we do in our simple deploy and create is we're going to do from scripts.helpful scripts import OpenSea URL. We're going to delete that here. So now in this script, this OpenSea URL is going to come from our helpful scripts, which is what we want. And we're going to do the same thing for our deploy and create for advanced. Okay, great. So I've now copied and pasted all the code from deploy and create into this deploy and create for our advanced collectible. So let's go ahead and modify this now. So instead of from Brownie import simple collectible, we're going to import advanced collectible. And we're going to do the same thing down here. And I'm even just going to go ahead and delete everything before this. We're going to change this to advanced collectible. And awesome. Okay, this is going to be our starting point. And we can even get rid of this sample token URI. Great. So this is going to be our new starting point. We've done a little bit of refactoring. Now OpenSea URL is going to be in the helpful scripts. We're pulling an advanced collectible instead of simple collectible. And the rest applies. We're still using our get account to get the account And now we have this advanced collectible equals advanced collectible dot deploy. Of course, our advanced collectible has a different constructor. It's got a VRF coordinator, a link token, key hash, and a fee. So we're going to have to add those as the parameters in here. We want to work with Rinkeby for this because the OpenSea marketplace right now for testnets only works with Rinkeby. So that's why we're going to work with Rinkeby here. So let's get started and just grab those Rinkeby addresses first. So our advanced collectible needs a VRF coordinator and a link token. So if we head over to the Chainlink documentation, we go to contract addresses for the VRF. We can scroll down to Rinkeby. We'll grab the VRF coordinator here. And same as before, we'll jump into our Brownie config. We'll do networks, Rinkeby, and we'll do VRF coordinator. We're also going to need the link token here. So we'll do link token. We need the key hash. And we need the fee, which is going to be 0.1 link, which we can do fee as 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, which is going to be 0.1. You can, of course, just copy and paste Brownie configs over to different projects because these values are always going to be the same. Now in our advanced collectible deploy and create, we can go ahead and add those variables in here.
Since we're going to be interacting with actual contracts that are on chain, and we're going to want to be able to flip back and forth between the mock versions of them, we're going to bring back that get contract function that we used before. This is the function that's going to be smart enough
to know if we need to deploy a mock or just grab from an actual contract.
I'm going to show a little fast forward of me rebuilding this function, but feel free to copy and paste it from our last project. Now, something that we do need to talk about though is our deploy mocks function. The syntax here is going to be basically exactly the same. However, we do need to deploy a couple of mocks, so make sure you have these in your deploy mocks function. Specifically, we're going to need a mock link token and a mock VRF coordinator. And again, feel free to just grab these from our last projects. And then, of course, be sure to
add your contract to mock dictionary, where the link token is mapped to the link token, and the VRF coordinator is mapped to the VRF coordinator. If you guys look in the GitHub repo, there's a couple try catches there that just make it a little bit nicer for error handling. But this is basically the entire script. So now what we can do, we can go back to our advanced collectible deploy and create, import this get contract from our helpful scripts, and we'll just replace this with get contract VRF coordinator. Get contract link token. And then for key hash and fee, since these don't really matter, these can be whatever we want, and these aren't really contracts, we can go back to our config. We'll add the development network, and we'll just add key hash and fee. And again, since it's just testing, we can just go ahead and make them exactly the same as Rinkeby. Whew, done a lot of work. Now, let's go ahead and run this on the development network again. So we'll do Brownie, run scripts, advanced, deploy and create, no network, so it's going to default to development. Let's see what happens here. And awesome. So we can see we actually did a couple of things here. So first, we deployed this mock link token. Then we deployed our mock VRF coordinator. We finished that, and then we deployed our advanced collectible all on a local network. So let's go ahead and continue here. Once we deploy this code, we're going to want to fund this contract with some link. The reason we're going to want to fund it with some link, of course, is so that we can call the random number. I like to have my funding with link also in a function. So we'll do fund with link, and we'll give it an address, advanced collectible.address.
And let's go ahead and create this function in fast forward. We're going to fast forward this as well, but feel free to copy and paste your fund with link functions from past projects. Or if you want to slow this down and follow along, feel free to do that too.
Let's go back to our deploy and create. We now have this fund with link that we're going to do right here. And then all we have to do now is call our create collectible function here. So we'll just do advanced collectible dot create collectible. Of course, from account. And we'll do creating TX. We'll wait one block confirmation. And then we'll print new token has been created. So we are definitely going to want to test this because we have a number of custom scripts here, right? So let's go ahead and just do a manual test. So we'll do Brownie, run scripts, advanced collectible, deploy and create, and we'll do it on a development network. Whoops, we got to add Ether here. Sorry about that. In the Web 3.2a 1 Ether. So let's go ahead and run the script again. And all right, it looks like everything worked. Everything was deployed. New token has been created. Great, this is fantastic. Now, ideally, before we do an integration test, we would, of course, write some tests.
But I want to teach some things that are easier to demonstrate on an actual testnet. So we're going to go ahead and deploy this to an actual testnet before we write our tests. So we're just going to run the script again
and do -- network rank B. And awesome, a new token has been created. So what we can do is we can grab the contract address once again. We'll paste it into the rank B Etherscan, and we can see everything in here. We can see we've given it a little bit of link. We can see our two function calls. One is going to be the contract creation. One is going to be create collectible. Our contract has already been auto-verified, actually, because I verified this contract on rank B already, and Etherscan says, this bytecode is the exact same of another contract that we've already verified. And if we go to read contract and we go to token counter, we'll see one token has been created. We've actually created our first token. Now what we can do in our advanced collectible scripts, we can create a new script and just call it create collectible. .py. And in here, we'll just create a collectible. So all we have to do is we'll do def main per usual. We'll have to do from Brownie, import advanced collectible. We'll import account from our helpful scripts. We'll import fund with link. In our main function, we'll do account equals get account. Of course, we need to import this as well from our helpful scripts. Then we'll do advanced collectible equals advanced collectible -1, because we just want to get the most recently deployed. We'll fund this contract with link. So we'll do advanced collectible.address. And we'll also choose an amount here. We'll just do web 3.2way 0.1 with Ether. So that means we also have to do from web3 import web3. Then we'll do transaction. Then we'll do creation transaction equals advanced collectible dot create collectible from account. We'll do creation transaction dot wait. We'll wait one block confirmation, and then we'll print collectible created. Oops, sorry, I actually don't have to import account here, or accounts, excuse me. And sorry, this actually needs to be amount equals, excuse me. Now let's go ahead and run this. And what we're going to do is we're going to fund our advanced collectible with link, which is 0.1 link. And then we're going to create a new NFT. Awesome, collectible created. So if once again, we take this address, go back over to Etherscan, do a quick refresh here. We go to our contract, read contract. We look at the token counter. It may still be 1, so you might have to give it a second for the Chainlink VRF to respond. Once the Chainlink VRF responds, we'll see 2 in here. We can also check the token ID to breed. If we look at the 0th one, we'll see the breed is 2. And if we look back at our contract, the advanced collectible.sol, we know that if the breed is 2, that means it's a St. Bernard. See the token ID of 1, it has a breed of 1, so it got randomly assigned a Shiba Inu. Awesome. So we have tokens and they get randomly assigned breeds. Fantastic. As you can see, we're doing kind of a lot of manual testing work here, right? So what we're probably going to want to do instead is, you guessed it, automate these tests. Now we can go ahead and want to deploy advanced collectible. So we can go ahead and import that deploy script that we just wrote. So we would do from scripts .advanced collectible .deploy and create import deploy and create. And then all we have to do is call deploy and create. In this function, we'd probably want to then return the advanced collectible contract so we can make sure that we actually get what we want here. So we'll say advanced collectible equals deploy and create. And that'll be our acting step. At the beginning, we'll do arrange. And then we'll do an assert of, we'll just check to see that the token counter has been increased. We'll do assert advanced collectible the token counter is equal to 1. All right, great. So this will return our advanced collectible. However, we know that since we're actually going to be working with a mock VRF coordinator, if we look at our advanced collectible, we know that the bulk of the work actually comes in this fulfill randomness function. And we're going to have to tell our mock to actually return and call this function. So in order to do that, we should probably also return this creating transaction here so that we can get the request ID. Remember how in our lottery, we actually just directly called everything. And we needed this request ID to call this callback with randomness function. In our tests here, we're actually using our scripts a little bit. So we could either just go ahead and write out all the steps similar to what we did in the lottery, or we could adjust our scripts a little bit. For simplicity here, we're just going to go ahead and have this deploy and create function also return the creating transaction. This way, we can go ahead and get the request ID. So back in our test here, that means we have to do deploy and create equals advanced collectible and creation transaction. Now that we have this creation transaction, we can use it to get our events. And again, if we look back in our advanced collectible, we can see here that we're emitting this requested collectible with request ID. So we can go ahead and do request ID equals creation transaction dot events. We'll add the name of our event here, which is requested collectible, and then we'll get that request ID. Once we have this request ID, we can then go ahead and grab the VRF coordinator. So from our scripts, we'll grab this get contract, and we've coded our get contract in a way that if the mock has already been deployed, again, if we go back to our helpful scripts, if the contract has already been deployed, then we're just going to go ahead and grab it. So since here, our mock will have already been deployed, so we don't have to redeploy it. So we can just do get contract VRF coordinator dot callback with randomness. And we'll use the request ID. We'll pick some number like 777. We'll give it to the address of our advanced collectible. And remember, we're going to be calling the callback with randomness. This is what a real Chainlink node is actually going to call back. And it just needs the request ID, the randomness number, and a consumer contract. So request ID, random number, and then the consumer contract. And then, of course, we have to do a from account, from get account. And we'll import get account as well. And now we can move into our assert phase. So first, if this is correct, then our token counter should be at least 1. So we can assert advanced collectible dot token counter is greater than 0. Or we could be a little bit more specific here, equals 1. we also should technically be able to get the breed and figure out the breed of this first token, of this first collectible. Let's go ahead and parameterize this 777. We'll call it random number equals 777. We'll place that here. And then what we can do is we can say assert advanced collectible dot token ID to breed of 0, right? In our fulfill randomness, we're going to assign the token ID to being the breed. And the breed is going to be this random number mod 3. So in our test, we can say the token ID to breed of dog0 is going to be equal to random number mod 3. And this is pretty much our full test. So let's go ahead and run this. We can do that test with -k. Whoops, it looks like our simple test has actually got an error now. We're getting this module not found. No module named scripts.deploy.create. This now, since we actually changed it, is going to be scripts.simple collectible.deploy and create. So now if we rerun our test, we'll see Brownie isn't going to error out anymore. So even though we skipped this test, Brownie still compiles it to make sure that everything makes sense. But what we see here is fantastic. Our advanced collectible unit test has worked perfectly. Let's go ahead and make an integration test for our advanced collectible here. So now we'll have our test folder here, and we'll have unit, and we'll have integration. Our integration test is actually going to look really similar to our advanced collectible here. So I'm just going to go ahead and copy everything. New file, test, advanced collectible integration.py. And we'll just paste everything in here. Now, the only thing that we're going to have to change is that we're not going to be the ones to call back with randomness here. So we can remove this part. We also don't need the request ID anymore since the Chainlink node is going to be responding. This means that the breed that we're going to get is actually going to be random. So we can get rid of that assert as well. All we need to do is wait for the transaction to get called back. So we're going to import time. And instead of us calling back with randomness, we're just going to do time.sleep. Then we'll wait 60 seconds. Test can create collectible. We should also give this a different name. Integration. Now we should be able to test this on a Rinkeby chain, and our token counter should indeed increase with the Chainlink node actually responding. So now we can run Brownie test -k, just that test -- network Rinkeby. Oh, whoops. Right now we're skipping this because we're saying only for local testing. Now, since this is going to be our integration test, we're going to do the opposite. If network.showActive is in these local blockchain environments, then we're going to skip it and say only for integration testing. All right, great. So now we have a quick and dirty integration test that we can run. We're not going to run it for now because we're going to be working a lot with this Rinkeby chain and we're going to be deploying a lot of different things. And we don't want to wait so long. So this is fantastic. We have a way to deploy this. We have a way to get these new collectible tokens and create them. But if we were to take this address right now and try to view this token on something like OpenSea, we would get nothing back. We wouldn't get any result. Right now, our token doesn't have a way to be viewed or be visible by everybody else. These NFT platforms don't know what they look like. And again, this is where that set token URI is going to come into play. So we have to figure out a way to host an image and host all the metadata for our token URI. And the way that we're going to do this is by using IPFS. And this is a lot better than actually hosting this on our own server because anybody can then go ahead and host this image or this metadata themselves. Now there's further improvements to this with something like Filecoin, where you actually pay to have your image hosted forever. However, IPFS can hook into Filecoin in the future and it is going to be a good enough solution for what we're looking to do here. Just keep in mind that what we do not want to do is run this on a centralized server. When we spin up our IPFS node, we will be the only node that actually runs and actually hosts our image. However, the image is open for anyone to pin to their nodes as well. So it's much easier for us to host our images in a decentralized manner. What's bad, obviously, is if we just had the image stored on our own centralized server, because if our server goes down, then that URL no longer exists. If at least one node on the IPFS network is hosting this image, it will be available for anybody to see. So that's why it's going to be a much better solution than some centralized server. As I mentioned, decentralized storage is a topic that's getting better and better, and we're looking forward to seeing more and more ways to interact with them. In any case, we need to create an IPFS node that's going to host some data that looks like this. Or, like what we saw with our simple collectible, it needs to host metadata that will look like this. We both have to host a metadata file and an image URI file, which will host the actual image. Both of these need to be stored on IPFS. So let's go ahead and create a new script called create metadata, which will read off chain and create our metadata file. So we'll start our scripts per usual with def main. And we'll get the most recently deployed advanced collectible using this -1 syntax. Of course, we're going to do from brownie import advanced collectible. Once we have this advanced collectible, we can then loop through all of the tokens and actually figure out the metadata for each one of them. So we'll do number of advanced collectibles equals advanced collectible dot token counter. Because we want this create metadata to create the metadata for every single token that we've created. Do a quick print line here, just saying print, you have created number of collectibles. We even run this really quick. Brownie run scripts, advanced, create metadata, network Rinkeby. Since we've already run this on the Rinkeby chain, we'll see you've created one collectible. If I were to run our create collectible script again, and then our create metadata script, we'd of course get more. But right now we only have one collectible. Now let's loop through all these collectibles and create their metadata. So we're going to create that file that looks like this, and it's going to have the name, which is going to be based off of the random breed that I got. It's going to have the description, which is based off of, again, the random breed that I got. It's going to have an image, which will also be based on the random breed that I got. And I just put some attributes in here, but again, these attributes. So we're going to say for each token ID in the range of number of advanced collectibles. For each one of these advanced collectibles, first we need to get the breed. So we're going to say the breed. The breed is going to be equal to advanced collectible dot token ID to breed of the token ID. Now, advanced collectible dot token ID to breed, this is going to return an integer, right? Because again, in our advanced collectible, this enum breed is going to be 0, 1, or 2. So we actually want to create a quick mapping that represents that 0 is Pug, 1 is Shiba Inu, and 2 is St. Bernard. So I actually like to create this in a helpful script called def get breed. And then it takes as an input, it takes a breed number, and it uses a switch statement. So up top, we'll say breed mapping equals 0 is going to be Pug, 1 is going to be Shiba Inu, and 2 is going to be St. Bernard. So in this get breed function now, we can just do return breed mapping of that breed number that we get. So instead of doing advanced collectible, the token ID to breed, we can now just do get breed. And this will return the number, and this will return the actual string. So we can just do from scripts helpful scripts import get breed. Now that we have the breed, we can start creating this metadata file. Now what we're going to want to do is we're going to want to have some type of format for our contract to always pull from. So what I like to do here is I'll create a new folder called metadata. And in this folder, I'll have a new file. called sample metadata.py. And then I just have metadata template equals, and then I just have this template that we're always going to use. Now in here, we're going to need a name, and then we're going to leave the name blank because we're going to want to fix it later. We're going to have a description, which we're also going to leave blank for now. We're going to have that image URI, which we'll also leave blank. And then we're going to have some attributes, which should be blank for this dog because we don't actually have any on-chain attributes, but I'm just going to go ahead and add some to show you what you could do if you wanted to give your dog some stats. You know, maybe cuteness, maybe raw power, maybe speed, agility, you know, whatever you want to do. So we'll do trait type, going to be cuteness, and then value is going to be 100. This would basically say, hey, there's a trait type called cuteness, and the value of that is 100. So the cuteness of the dog is 100. So now once we have this sample metadata file, we can import this into our script here. So we'll say from metadata dot sample metadata import metadata template. And another quick note, you might have to put a __init__.py file in that metadata folder if you're working on older versions of Python. And we can start creating our new metadata file for this breed, for this dog. We'll want to save each collectible under their network and with their token ID. So let's go ahead and create a new folder. We'll call it RinkB, and this is where we'll save all of the RinkB metadata for all these collectibles, for all these token IDs. Now, before we actually save it though, we should just check to make sure that the file doesn't already exist, right? Because if the file already exists, that means we've already created the metadata for that token and we don't need to. So we can just go ahead and get the metadata file name, which is going to be equal to /metadata /network.show active. Of course, this means we need to import network from Brownie / the token ID with a hyphen with the breed.json. Just to make sure we're doing this right, we can even just print this out. Do a quick manual test. Brownie runs scripts, advanced, create metadata, network RinkB. So this will be the name of the file. So metadata, RinkB, token ID, and then the breed.json. Okay, cool. Now we can actually check this to see if this already exists. And we're going to use a Python library called path. So we're going to say from pathlib import path. And we're going to say if that path, this metadata file name dot exists, if that path exists, we'll do a quick print saying metadata file name already exists. Delete it to overwrite. This way we won't accidentally overwrite metadata that we've already created and do extra work. So if it exists, we'll print that out. Great. Otherwise, we can go ahead and printf, creating metadata file name. We can even run this real quick. Great, you have one collectible, creating metadata file. Perfect. So let's go ahead and start creating this metadata file. So we're gonna have to give it a name, description, image URI, and we're not gonna give it any attributes though. So just name, description, and image URI. So name is easy enough. Since this is a dictionary or a mapping in Python, we can actually just go ahead and start mapping. So up above before this if, we'll do collectible metadata. It's going to be equal to this template. So this is going to be where we store all of our metadata. And we'll say collectible metadata of name is just going to be the breed. So if it's a pug, the name will be pug. If it's a Shiba Inu, name will be Shiba Inu. If it's St. Bernard, name will be St. Bernard. And we'll give it collection metadata description is going to be equal to, we're going to do an F string here, and adorable breed pup. Now, if we print out this collectible metadata, we should see at least the start of the metadata, which we do. Great. Name, St. Bernard, description, an adorable St. Bernard pup. Of course, you'll have a different random breed, but it should look something like this. Now, we're going to need collectible metadata, image URI. This is where we're going to have our image already uploaded to IPFS so we can assign it to our metadata here. So how are we going to do this? Well, we're probably going to need some upload to IPFS function. It's going to return our image URI. And then we can just set that image URI to the collectible metadata of image. So let's go ahead and start doing that. Let's create our upload to IPFS function. Now, in order to upload to IPFS, we of course need to have the images ourselves. I already have them downloaded here. And again, you can download them right from the GitHub yourselves if you like. To make this a little bit generic, we'll have this upload to IPFS take a file path. That way we can pass this image URI upload to IPFS. We're going to give it some type of file path here. We're going to have to grab that image path. So we'll grab that image file name by just doing breed dot lower. Because right now our breeds are all uppercase. So we're going to want to make it lowercase. Then we're going to replace the underscores with hyphens .png. So we'll say plus .png. And then, you know what, let's just go ahead and add the full path here. So we'll say /image / plus breed.lower. Perfect. So, and then we'll even change this to image path. And then we can pass this to our upload to IPFS. So this file path now is going to be the location of the object that we're going to upload to IPFS. We're going to use this path library to actually grab that path to upload it to IPFS. So we're going to say with path, file path, dot open RB as file path. Now this is a little bit of sophisticated Python here. What we're doing is we're taking this path here, we're opening the file. RB means we're going to open it in binary. Since these are images, that's how we're going to actually open it. And we're going to upload the binary actually to IPFS. And then as FP, so we're saying this opened file is going to be named FP or file path. We're going to do image binary equals fp.read. And that's how we actually read the whole binary. And now this whole image is stored as binary in this image binary here. Now here's where we're going to do the upload stuff. Now to get started here, we're actually going to have to download the command line for IPFS. Download command line IPFS. We'll come right to the docs here. And again, there's going to be a link in that GitHub. And in here, there are instructions to download it for whatever system that you're working on, right? If you're working on Windows, if you're on Linux, if you're on Mac, these are the different ways to actually download this IPFS command line. You'll know you've done it right if you can type IPFS -- version and you see something like IPFS version 0.9.0. It's important to note that we could also do the IPFS download desktop, and we could download the desktop version of this, and we'd see a user interface which looks something like this. We could upload our files manually and then manually go ahead and grab those files and place it into our scripts. But we're engineers, we want to do this programmatically. In any case, once we have this API downloaded, we can actually follow the documentation here, the HTTP API reference for actually uploading our code. We're going to be mainly working with this endpoint API v0/add, as this is the endpoint that's actually going to add our file or directory to IPFS. Now, what we're going to want to do is we're going to actually upload our images to our own IPFS node. We can run our own IPFS node by doing IPFS daemon. And we'll see an output that looks something like this. We can even see a web UI using this web UI URL here. This will look similar to what the IPFS desktop looks like. But again, we're going to work just mainly from this daemon from our own IPFS node. Congratulations, you're running your own IPFS node right now. As you can see, it's currently running on our own local host right here, HTTP 127.0.0.1 at port 5001. So to actually upload this, we first need to get that IPFS URL, which is going to be equal to this URL right here. Paste. Now we want to make an API call or a post request to this endpoint using this API v0 add. And these are all the different parameters that this add can actually take in so that we can actually post it to IPFS. For those of you familiar with curl and you want to test this out using a curl, I've added a curl into this create metadata file as a comment so that you can actually go ahead and test this if you want to use this. Now what we're going to want to do to keep working with our scripts is you should have like a little plus button somewhere on your VS Code. We're going to hit that plus button, and now we're actually going to have two different shells. One which is running our IPFS node, and one which is running our bash or ZCH or whatever other shell that your OS natively works with. Now that we have this IPFS URL, we're going to grab the endpoint, which is going to be, again, this right here, -API -v0 add, and we can make a post request to it. So for us to do that, we're going to say response equals requests.post. We're going to do the IPFS URL plus the endpoint, and we're going to say the files that we're going to upload is going to be equal to file image binary. Requests is a Python package that we're going to import. So we're just going to say import requests. Now, if we go back to the IPFS documentation, we can scroll down to see what the response looks like. It's going to return a bytes, a hash, a name, and a size. Now, if we look at this sample token URI, we can see the API call here. IPFS stores all its data using a hash. And if we're looking at this, the simple collectible, this hash here is the hash that represents this pug.json file. Everything in IPFS gets hashed, and every single piece of data has a unique hash, which is why it's so fantastic. If we were to change anything with this image, this hash would be drastically different. All we need to do is get the hash that IPFS gives the image that we upload, and we can go ahead and plug it into a template URL like this one here. So what we're going to do then is we're going to say IPFS hash is going to be equal to this response.json, since we're just going to JSONify the response to make it look like this response here. And we're going to grab that hash, right? Since it's going to return this dictionary. And we just want the hash here. Then we're going to give it a file name by saying it's going to be that file path dot split. We're going to do some fancy Python stuff here. We're going to say -1 to 0, which basically all this line is doing is saying, you know, if we have ./image/pug.png, we're going to split it up by these slashes into an array, and we're going to grab the last part of the array. So we're basically just changing this to this with this line right here. Then with this, we can get the image URI, which is going to be equal to an F string again, https ipfs.io/ipfs/ipfs hash file name equals file name. And it's this format right here which will give us this. So if I go ahead and even just copy paste this under as a comment to show you guys, we see this part's exactly the same. And then this is that hash here, represented here. And then we have file name equals, and then the file name. So excuse me, this is actually going to be like 0-pug. And that's exactly what we need. We need this image URI. So we'll do a quick print image URI. And then we'll go ahead and return that image URI. Now, since we're actually going to be testing this with IPFS, we can add a new integration test. So we'll call this test IPFS upload.py. Now, you might want to write a test for this, and we're not going to do one, but I challenge you to later on maybe come back and and write your own test for this upload to IPFS. For now, we're actually just going to manually test it. So we're going to go back up to our script here, and we're going to run image URI equals upload to IPFS image path, and then we're going to get printed an image URL. Since we're working with the St. Bernard here, we should get a St. Bernard image URI. So if I run Brownie, run scripts, advanced, create metadata, network Rinkeby, let's see what happens. I needed to add brackets here. Sorry about that. Now let's try it again. Awesome. We were able to create this metadata file. Now, if we go ahead and copy this and paste it, perfect. We see exactly what we're looking for. We see our St. Bernard. Awesome job. And this has been uploaded to our own IPFS node. Now, I want to show you guys actually another service and another way we can actually upload these to IPFS. Some people don't want to run their own IPFS node because they're not actually going to be keeping it running the whole time. Anytime their node goes down, this means that nobody will be able to see your image unless somebody else pins your image or uses your image. So what I also like to do is I like to upload it to some other third-party service as well as uploading it to my own IPFS node. So I like to create another script actually called deploy to Pinata. So let's go to scripts, new file, upload to pinata.py. So Pinata is an IPFS file management service, and they actually will pin whatever files that we're working with as well. So we'll have it pinned in our node, and they will have it pinned as well. So we can go ahead and register. Awesome. This is what Pinata looks like. It's a way to upload and work with IPFS, and they'll give us some extra support. And they have a free tier, which is fantastic as well. They have some wonderful documentation as well under this documentation section. So let's go ahead and upload this to IPFS so that when our node goes down, our images don't go down. So we'll do Pinata base URL is going to be equal to https://api.pinata.cloud. You can find all this in the documentation as well. If we scroll down the documentation, we're going to be using this pin file to IPFS endpoint here. And you can see that entire endpoint right here with the base and then the endpoint. So we're going to copy that endpoint. We're going to say endpoint equals pinning/pin file to IPFS. We're going to choose some file path. And for us, we're just going to do ./image/pug.png. Of course, if you want to upload some other image, you could, change this file path, or you could even do some type of for loop to pin everything in the image section here. Again, we're going to do file name. We're going to use that same syntax as before. We're doing file path .split / some fancy Python stuff just to get this last part. And we also need to use some headers in this post request. So it's a type post request. We need to use some headers here. So we're going to say headers equals, copy this, Pinata API key, which is going to be some API key. And then we also have this Pinata secret API key, Pinata secret API key, which is going to be something else. We can find these two API keys. If we scroll all the way down, we hit API keys, create a new API key. I'm going to call this, you can make this an admin key. I'm just going to do limit max uses. I'm going to set this to 200 because I'm going to make this a public key, so I don't want people using this a million times. Please make sure you select at least one permission. Pin file to IPFS. For those of you guys watching, you can absolutely just grab all of these if you want. You can make this an admin, do whatever you want to do here. Since I'm only going to be using this pin file to IPFS, that's all I'm going to do. Hit create key, and here are our tokens here. So our API key is going to be right here, and we're going to copy that. We're going to open back up that .env and add this as one of our environment variables here. So we're going to export Pinata API key equal to that key there. This API secret we're going to copy, and we're going to do export Pinata API secret equals that key there. And we actually don't need this JWT, but if you guys wanted to, you could copy it as well. So now that we have them in our .env file, these are now going to be environment variables that we can use. And Brownie is going to automatically put them into our environment. So what we can do then is we could do os.getEnv Pinata API key. And then, of course, we're going to have to import os. And then for our secret key, we're going to do the same thing, os.getEnv Pinata API secret. And this is how we get those two headers for uploading to Pinata. Then we're going to do a lot of the same code we did before. We're going to say with path of file path.open RB for the binary as FP. Of course, since we're using path, we're going to do from pathlib import path. We're going to do the same piece, image binary equals fp.read. Response is going to be equal to requests, which we have to import requests. Import requests. .post Pinata base URL plus that endpoint that we have. And for files, it's going to be equal to file. And we're going to upload a couple of things here, though. We're going to give it a file name. We're going to do the image binary. And that is getting really annoying when it keeps getting in the way. File name, image binary. And then outside of these brackets here, we're going to do comma, headers equals headers. And then we're just going to print response.json. So to have this run in Brownie, we're just going to do a def main function here. A nice little trick we can do is we can select all this text and just hit tab and it'll move it over one. And perfect, we can now run this inside of Brownie. So we can do Brownie run scripts, upload to Pinata, and perfect. We get a little output that's going to look something like this. It's going to give our IPFS hash, the pin size, the timestamp. So now if we go back to Pinata, we go to pin manager, do a little refresh here. We now see our pug has actually been uploaded to Pinata. Awesome work. We're going to keep going using the IPFS daemon to actually upload things. But if you want, you could totally swap out this upload to IPFS to use that script that we just created to upload it via Pinata instead of our own IPFS node. Anyways, this upload to IPFS is going to return this image URI. So we can go ahead then and set the image URI. It's going to be set on this collectible metadata image. And then all we have to do is dump this collectible metadata into its own file and then upload that as well to IPFS. We'll dump this to its own file by doing with open metadata file name, and we open it with a W, which means that we're going to write as file json.dump collectible metadata to the file. So we're going to have to import JSON to do this. And what this is going to do is just going to dump this dictionary as JSON to this collectible metadata file. Then we can upload to IPFS also this metadata file name. And this upload to IPFS should print out the image URI, or in this case, the metadata URI. So let's go ahead and try this out. So remember, we do need our IPFS daemon running. And let's go back to our scripts and we'll do Brownie, run scripts, advanced, create metadata, network, rank B. And boom, okay. So here is our image URI, which if we click this, we'll be able to see looks just like this. And then here is our uploaded St. Bernard metadata file, which is fantastic. So now we have both a metadata file and we have an image URI. This is fantastic. We've uploaded both of these to our IPFS. And if we scroll over, go to our metadata file in RinkB, we'll see we have this new file in here because we've gone ahead and saved it in here. it has everything that we need. It has St. Bernard, it has the description, it has this image URI that we just created, and it has some attributes that, again, we're basically ignoring. Now, to make our lives a little bit easier, and since I've already actually uploaded these to IPFS myself a couple times, and since the hashes of these are going to be the exact same for all of us when we upload this, we're going to go ahead and just quickly refactor this to make it a little bit easier so we don't always have to have IPFS running. So in our .env, I'm going to add a new environment variable called upload IPFS, and we're going to set it equal to false. So now down here, I'm just going to say if os.getEnv upload IPFS equals true. Anyway, since we're going to do OS here, we're going to do import OS. And before this, I'm even going to do image URI equals none. And we're going to say image URI equals image URI if image URI, which again, I know this can be a little confusing, but we're setting image URI to whatever image URI is. If image URI isn't none, else we're going to create a mapping called breed to image URI of the breed. So again, since I've already uploaded them, I already know what all these image URIs for these 3 dogs are going to be. So up at the top, we're just going to create a new mapping called breed to image URI equals. I'm actually just going to go ahead and copy paste this whole thing. Now you can skip this. You don't have to refactor here. And you can just always have your daemon running and always upload to IPFS. It's a little bit quicker to not always have to do that. Again, this breed image URI is in the GitHub repo. Feel free to just copy paste it to use it. You can even click the links to check it, check to see that those image URIs are really there. And this is what we'll use. So back down here, breed to image URI, perfect. And then we're also going to add if, again, os.getEnv upload IPFS equals true. Then we're also going to upload to IPFS down here. But this is to go and actually just show you how exactly we could upload all this stuff to IPFS. Since I've already done it, we're going to make it a little bit easier on ourselves. Another thing that you might do is you might actually save all these URLs to their own file, to their own JSON object, maybe inside of the metadata folder, maybe under Rinkby or something. And then you could go ahead and just pull directly from those files. Same thing with the metadata. Once we upload to IPFS, we're not actually going to save these URLs anywhere. You could absolutely 100% after you run this upload to IPFS script, we could go ahead and save it to a file and pull directly from there moving forward. But awesome. Okay, so we've done a lot of work here. We have uploaded to IPFS our metadata and our image URIs. So we have everything that we need to actually just set the token URI finally for our advanced collectible. We finally can call this set token URI function. So let's go ahead and do this last bit here, this last set token URI function. So let's go to scripts, advanced scripts, create a new file. We'll call it set token URI, URI.py. And this is where we're going to set the token URI. So we'll do def main. And then here we'll do a quick printf, working on network.show active. Of course, since we're using network, we'll do from Brownie import network. We need to close that there. And let's grab the most recent advanced collectible, which is going to be equal to advanced collectible -1. Since we're using advanced collectible contract, let's import that from Brownie. Let's once again loop through all the tokens that have been deployed. So we'll do number of collectibles equals advanced collectible dot token counter. Do a quick print. You have printf, excuse me. Number of collectibles, token IDs. And let's loop through this list of collectibles again. So we'll say for each token ID in range, number of collectibles. First, we'll get the breed, saying breed equals advanced collectible token ID to breed of the token ID. We actually have to call this get breed function again, which luckily we generalize, so we can do from scripts.helpful scripts import get breed. And now let's first, before we actually set the token URI, let's check to see if it already has a token URI set. So we're going to say if not advanced collectible.token URI of token ID dot starts with HTTPS. So what this line is doing, I know it's a little bit long, is we're grabbing advanced collectible.token URI of the token ID. So we're grabbing this token ID's token URI. And we're saying if it doesn't start with HTTPS, that means we know that it hasn't been set. So we can go ahead and print setting token URI. Let's actually make this a printf of token ID. And then we can set the token URI. So I'm actually going to generalize this out into its own function. So let's go ahead and we'll do def set token URI. And as inputs, this is going to take the token ID, the NFT contract, which is going to be our advanced collectible contract, and the token URI. So the first thing that we're going to do, we're going to say account equals get account. So we're going to grab this get account, of course, from our helpful scripts, because this set token URI is actually going to call that set token URI function. We're going to say NFT contract dot set token URI of the token ID and the token URI. Remember, this is a function that we added to our advanced collectible right here, set token URI. It takes a token ID and a token URI. And this is going to be from, of course, the account we just created. So we're going to say transaction equals that. We'll do transaction.wait. We'll wait 1 second for it, or 1 block for it. And then we'll print, we'll do printf. Awesome. You can view your NFT at, we use that OpenSea URL, .format, NFT contract.address, comma, token ID. And then I'm just going to add another print here saying, please wait up to 20 minutes and hit refresh metadata. Hit the refresh metadata button. So now we have our set token URI function. We can add the token ID in here, the advanced collectible contract, and then we just have to add the token URI here. So since we've already uploaded, and since I've already actually uploaded all three, what you could do, and what I like to do, is just have a dictionary here so we don't always have to be pulling from something. So I have a dog metadata dictionary. It's going to be equal to, and we're going to add those different dogs in here. So St. Bernard, this St. Bernard URL. We're going to paste it here. I've actually gone ahead, like I said, and uploaded this metadata for all three dogs. So I'm just going to go ahead and copy paste all three in here. Again, we're shortcutting a little bit here, but what you could do is you could save all these metadatas to their own file, and you could just pull from that file instead of doing kind of this dog metadata dictionary. So in any case though, we're going to do dog metadata dictionary of breed, right? Because dog metadata dictionary of St. Bernard is going to be this, which again has our image URI, has everything about our dog, and is perfect. What we also might want to do is write some tests around our set token URI function, of course, but I'm just going to move on. So in any case, we've done a lot here. I'm actually going to even close down my IPFS node, and we should be just about ready for everything. So of course, we'll run our Brownie test. Want to make sure that all our unit tests are working great. which they look like they are working fantastically. But we are ready to do a full end-to-end manual test here. And you could 100%, and I actually highly encourage you to 100%, we're just going to run these scripts in order and look to see if our stuff shows up on the OpenSea NFT marketplace. So, are you guys ready? Let's do this. So make sure, of course, your environment variables are set here. Make sure that your MetaMask for Rinkby has some ETH and has some link, and then we can go ahead and start running some of these scripts. So we'll do Brownie, run, scripts, advanced collectible, deploy and create, network, Rinkby. Integration test moment of truth. And perfect, a new token has been created. Awesome. We can even go grab this address. Let's delete all these tabs that we have opened up. And we'll go to rinkby.etherscan.io. We'll paste it in here. And we can see contract has been verified, even though we didn't verify it because it matches some other source code. We can see token counter is 1. And we can even go to token ID to breed of 0, see what breed it is. So it's breed 2. And it looks like we're getting a St. Bernard again, which is incredibly adorable. We can even go to events here and we can see the different events. Since this is verified, we can even see the name of the events. So we have our breed assigned event and we have our requested collectible event. First is an index topic of token ID, and then there's the UN8 breed. And then we have the bytes32 request ID and the address requester. Now, let's run our create metadata script here. So we'll do Brownie, run scripts, advanced, create metadata, network, Rinkby. We don't have to run create collectible since our deploy and create already does that. So now if we run our create metadata, since this is a St. Bernard again, I'm going to go ahead and get this already exists, delete to overwrite. So what I'm going to do is I'm actually going to even create another one so that I get a new NFT. So I am actually going to run this create collectible script. So we're going to do Brownie, run scripts, advanced collectible, create collectible, network Rinkby. And what this is going to do, all it's going to do is it's going to fund with some link, which it's going to be a little bit overkill with the link, but that's fine. And then we're going to do advanced collectible.create collectible. So we're just going to do 2 transactions here. Perfect. Collectible has now been created. Now I'm going to wait a solid 30 seconds to have that Chainlink VRF respond. And I'm even going to go to the contract, give it a quick refresh. Look at this token counter. Once the Chainlink VRF responds, this token counter will then be 2. Now that I see a token counter of 2 here, that means that it actually has responded. So we can now run the create metadata script. And we should have a new metadata file now. You have 2 collectibles. 0 St. Bernard already exists. Delete it to overwrite. Create a metadata file. Metadata Rinkby pug. So now if we look in metadata for Rinkby, we have a St. Bernard and we now have a pug. Awesome. So we're going to set the token URI of both of these. If I grab this contract and I go to testnets.OpenSea, testnets.OpenSea, I can paste this address in and I'll get this doggy and then this random hash here, right? And we see there are 2 token URIs deployed. Again, if they're not here, you might have to refresh, but they don't have the images, right? Because we haven't set the token URI. So we'll go back, we'll look at the advanced collectible. We've deployed and created. We've created another collectible. We've created their metadata. Now all we have to do is set the token URI. So Brownie, run scripts, advanced collectible, set token URI, network Rinkby. And the script, it's going to loop through all of them and actually going to set those token URIs. So we have setting token URI of 0. So this transaction is doing exactly that. And it's going to go ahead and say, awesome, here's your output. And then it's going to say setting token URI of token ID 1. And that's that second transaction. And it also gives us an output to that one as well. So if we've done this correctly and we hit refresh metadata on this testnets.OpenSea.io and we do a little refresh here, we can now see our St. Bernard, which is fantastic. And then if we change this from 0 to 1, since I've deployed 2, and I refresh this one's metadata, and then refresh the page, we can now see the pug as well. Again, just keep in mind, sometimes the refreshing metadata does take some time, and you might have to wait up to 20 minutes. But for all intents and purposes, we have just deployed our NFTs, given them token URIs that aren't around centralized servers. We can now see them on an NFT marketplace like OpenSea. You can let out a big sigh of relief because you just did something fantastic that not a lot of other engineers can do. You should be incredibly proud of yourself at this point. Let's take a minute, go back over some of the new things that we've learned here.
Take a quick minute to really celebrate how far you've gotten because you are doing absolutely phenomenally. So that was the NFT lesson. There are tons of ways to make really, really cool, really fantastic NFTs. And this is really just the smallest piece of what you can begin to do with this NFT technologies. Now, remember I said the next 2 lessons are going to be optional for the Chainlink YouTube here. You can absolutely go check them out, go into the freeCodeCamp video, go watch those videos, or jump into the description and see some more of those videos and some more of those tutorials on these concepts because they're going to make you a lot better as a smart contract engineer. But for the purposes here, you're all done. Huge, huge congratulations for what you've accomplished. You've done amazing to get this far. And I look forward to seeing you in the blockchain space, seeing you in the community, seeing you at some events. Congratulations, best of luck, and we'll see you next time.